Good. All right, let's go. All right, so let's remind ourselves what these things are. It seemed to be a little bit confusing the last day about modulus, conjugates, the combination of moduli and conjugates, which this was. Let's just remind ourselves what that means. So we have a complex number, z is a plus bi. We see this terminology a bit, z with the two lines either side of it, which is the modulus one. The modulus of a complex number, let's say this is a here and this is b. So we have a real and imaginary. The modulus is measuring this distance, yeah, from the origin to wherever the complex number is. So it's going to be a positive number. How we do that is we use Pythagoras' theorem, a squared plus b squared, and we square root it to get this hypotenuse side squared. Yes? Make sense? Abby, you still don't have glasses?
No.
Wonderful. So the conjugate, which is this other symbol, the conjugate of a complex number is its kind of opposite. It helps us a lot when we're trying to realize the denominator. We multiply by the conjugate numerator and denominator, and that will realize the denominator. Okay, so that's the conjugate. Graphically, what does it look like? Yeah, geometrically. So if this is a plus bi here, over here? No, down here. Yeah. So it'd be here, a minus bi. It'd be a reflection in the real axis. Yeah, it'd be the opposite side of the real axis. Okay, and our homework included some questions that we had to prove, and then some questions we had to solve. Let's look at the proofs first, which was question 6, maybe. Okay. So what we're trying to prove here is that the modulus of the conjugate is the same as the modulus of the original. Now looking at our diagram, this is the modulus of a complex number, and this is the modulus of its, drawn badly, this is the modulus of its conjugate friend. They should be the same length, because it's just a reflection. There's no reason why, like b has not changed in length. A and A is the same for both. So geometrically, they should be the same. Make sense? Okay. How would I prove that? Just do it, yeah. So we'll use this complex number as our example. So we can always use a plus bi or x plus yi as our example. So a plus bi. Now this, of course, would be a minus bi because it's the conjugate. So we're going to get the modulus of this complex number and the modulus of this complex number, the distance back to the center. So to get a modulus of something, we do this process, a squared plus minus b squared, if you want to do that, square root. And does that equal a squared plus b squared square root? So we're looking at this distance back, and this distance. And the b squared turns positive, and you're there already, aren't you? Because a squared plus, that's just positive, and you're already proved. Left-hand side equals right-hand side. Okay, all good. All right, so that's true. Now this second one is true, and this one was crucial to the way Philaine solved question 15, 13. Yeah. You use that to solve all, and I used a different method and had forgotten about this property, but we got to this property now. All right, so we have to prove it first, and then we can use it. So what we're proving now is that if I got the modulus of this, and I squared it, so let's give it a numerical value. Let's say that this was 5. And if I squared it, so 25, would it be the same as multiplying this by this? I'll just say it again. If I got this number, I put a numerical value at it, 5, and squared it, the modulus, and then square it, will it be the same as multiplying this by this, which is... Yeah, I think so.
They're the same anyways.
Yeah.
In terms of modulus, they're the same.
Okay. Now, So that's true. That's one of the ones that I'm not proving. What about this one? If I take the modulus of this, and let's say it's 5 again, will it equal the two complex numbers multiplied? The 8
Well, because
by
the
its
linearities
mod.
cancel out when you multiply by their conjugate, right?
So
So it should be this.
should it?
Yeah, because there's a plus bi and a minus bi.
Okay.
And when because you're multiplying the plus bi, the plus bi and the minus bi.
So what we proved earlier geometrically was, actually I'll put it up in a second. I'll show what it means in a second. But we'll prove this one now. And we'll do this with actual complex numbers again. So we'll do, okay, is A plus BI the conjugate, or not the conjugate, the original? If I get the modulus of this, its distance, and then square it, will it be the same as just the two complex numbers multiplied by each other? So A plus BI times A minus BI. So we're trying to get the left-hand side to equal the right-hand side here, which you did for homework.
Yeah, 100%.
Did it work? Yeah. Did it work out for homework? Some of you. Yeah. Okay. So let's get the modulus of this. That's A squared plus B squared, yeah? And I'm going to end up squaring that, which you may see something's going to cancel. It's just going to be this and this canceling. So we got A squared plus B squared. Okay, let's work with the right-hand side and get it looking like that. A times A is A squared. A times, well, you kind of know this, but we'll do it anyway. ABI plus ABI. Yes, minus B squared I squared.
And then I squared is minus 1.
Now these cancel, and minus B squared I squared. I squared is minus 1, so you get that changes. A squared plus B, so it is equal. Now how does that help us with the example we had on, we'll only do one of, yeah?
Can we just do A?
Hmm? Yeah, in that one, yeah.
Just do A or B, sir, to make it faster.
No, we will do the one that was causing more problems. Yeah.
But like in principle, it's the same thing.
In principle, there are some of these, and I found where they were. Where's my clicker? There are some that are